Hello, good morning. Can everyone hear me?
Yes, good morning, sir.
Okay, good. So let's start our class. It's 8 a.m. and today our class is for 1 hour, right? Please make sure that you have scanned your attendance on e-learning. I have uploaded the QR code on e-learning, so please scan. So today we will start with our new chapter, chapter 5. So what was chapter 1? Chapter 1 was introduction. Let me quickly check. Chapter 1 was introduction. Chapter 2 was representing position and orientation. Chapter 3, mobile robots. Chapter 4 is robot arm kinematics. And now chapter 5, planning of manipulator trajectories. I have not uploaded the slides on e-learning yet. I will do it today. Oh, I need to share my screen. Sorry about that. Okay. So I hope you can see my screen. Alright, so we now turn to the problem of controlling the manipulator so that it follows a pre-planned path. Before moving a robot arm, it is of considerable interest to know whether there are any obstacles present in its path that we call an obstacle constraint, and whether the manipulator hand must traverse a specified path. This is what we call the path constraint. Okay, I'm going to show my sketchbook. So imagine you have a robot arm, perhaps something like this. Sorry for my bad drawing. Okay. So this robot has 1, 2, 3, 4 joints, right? And we want to pick something. And normally we would have some sort of fixture, right? To hold our object to be picked. So let's say this is the object. Okay. So this is fixture. So fixture holds the object to be picked, and this is our object. And let's call this pick location. Okay, so we want to pick this object, and of course we want to place it somewhere else. And similarly, we would have fixture, and we want to place that object at the fixture. Okay, so you can imagine when we want to pick the object, our end effector should be should be here, right? And I don't want to draw the robot, but the n effector should be here, and we're going to place it. The n effector should be somewhere on here. Okay. And of course, in order to have this, we need to have the robot in a certain configuration as well. Okay, so the robot has to be in a certain configuration. Okay. So from here to here, so you can imagine the robot will be in various configurations, and in various, the position and orientation of the n effector will change from here to here. So this is what we call a path, right? From whenever the robot moves, for example, in this particular problem, to pick an object and to place an object somewhere else, it has to follow a certain path. All right. So you know that in order to have the pose of an effector, you need to have various configurations of the robot. Okay. And this in turn is caused by various angles. So what I'm trying to say here is that for various robot arm joint angles, you would have various robot arm configurations, and in turn you would have various pose of an effector. I hope you can imagine this, right? So if, for example, if you change theta 1 over here, the configuration of the robot will change, and therefore the position and orientation of the n effector will change. So back to our pick and place operation or motion. When we pick our object from here, and then we move to the place location, we can imagine the pose will change, which is caused by the change in robot configuration, which is caused by the changes in joint angles. All right, so if I could, if you imagine, if we could plot let's say if I plot theta 1, so this is time and this is theta 1. So you can imagine it changes. So maybe this is pick time, the moment we picked our object, and this is the place time, right? Later you will see that we will call this initial time and this is final time, and this will be our initial position and this is final position. Okay, we will talk about this later, but for now let's call it peak time just to suit with our diagram. So this is the moment we picked the object, and this is the moment where we placed the object. Okay, and you know that theta 1 will change, only this theta. Similarly, all other thetas will change as well. Okay, we can plot the same type of graph for all joint angles. So it will have its own trajectory. So this is what we call the path. This curve is what we call the path or the trajectory. Path or trajectory. Okay, so let's get back to our slides. What does it say? So this chapter focuses attention on various trajectory planning schemes for obstacle-free motion. So we assume that in this chapter, when we move our robot, we don't have any obstacle present in the middle. Even if you have obstacle, you can easily navigate around it because you can have two trajectories around, maybe trajectory 1 to avoid the obstacle and trajectory 2 finally to reach your place location. So it's not a concern whether we have obstacle or not. It deals with the formalism of describing the desired manipulator motion as sequences of points in space, though which the manipulator must pass, as well as the space curve that it traverses. So in our trajectory planning, we describe the path as sequence of points. So if you look at this graph here, indeed it is a sequence of points. Okay, and the overall sequence of points, it does produce some kind of curve. So it doesn't have to be, it can be any curve, right? If you think about it, it can be a straight line from here to here. It can be 1 minus exponent, any path, right? But it has to be suited with our application. In our case, we are dealing with a robotic arm. So you can imagine if you move from here to here in a straight line, there are consequences. So maybe you will cause some form of jerking of the joints, which normally we want to avoid. And that's the space curve that the manipulator hand moves along from the initial location, position, and orientation. Remember in chapter 2 we call this pose, right? So position, orientation here is referred to as location, but you know it's also called pose. To the final location or pose is called the path. So like I said earlier, these are the path, and for every joint we have a path. Effectively, in order to produce this motion right here, so that the end effector move from one pose to another pose. Okay, but so in order to do that, we need to have the path for every joint. So in this chapter, we are interested in developing suitable formalisms for defining and describing the desired motions of the manipulator hand between the path endpoints. Right? To servo a manipulator, it is required that the robot arm's configuration at both the initial and final locations must be specified before the motion trajectory is planned. Okay, so like I said earlier, right? So in order to design a path or trajectory for a robot arm, we have to determine the pose of our end effector, the initial pose, and the final pose of the end effector. So from here, if we go back a step, we will get the configuration, and if you go back a step, we will get the joint angles. And then we'll do our computation of the actual designing of the path with these values. Right? We will see later how we can do that. So in planning a joint interpolated motion trajectory for a robot arm, so we call it joint interpolated because we'll be planning or designing the path for every joint angle. So when picking up an object, the motion of hand must be directed away from an object. Otherwise, the hand may crash into the supporting surface of the object. Okay. So if we look at this, right? So imagine this end effector goes down and it picks this object, and from there it moves directly to the place location. What will happen? So probably it will hit the fixture and damage the fixture and probably the robot arm itself. So normally after picking an object, we want to move straight up first just to clear the fixture and then move to another pose or another location and then slowly lower the end effector to place the object. So we have 4 different poses here, right? So you can imagine you start with picking, that's one pose, and then you move to another pose here, which is away from the fixture, because we want to avoid hitting the fixture when we start to move. So we move it up here, that's second pose. You move to the third pose, because if you move directly to the final pose, you will again hit the fixture. So you will move slightly away from the fixture, that is the third pose. And the fourth pose is the final pose where you lower the object and release it or place it. Okay, so that is what these 2 points are saying. So if we specify a departure position, which we call lift off point, along the normal vector to the surface out from the initial position, and if we require the hand or the end effector to pass through this position, we then have an admissible departure motion. If we further specify the time required to reach this position, we could then control the speed at which the object is to be lifted. So from those 2 points, now you know that this is the initial. So we have number 1, we have initial position. We have initial position. Number 2, we have the lift off position, right? Lift off. Okay, lift off position. You can imagine, so this is your initial position. Let's call this initial position theta 0 here, right? And from here you have to move up, normally straight up from the surface, right? Normal to the surface, straight up, because we want to avoid hitting the fixture, and that is what we call the lift off position. Let's say it is here. So this is theta 1. So this is theta 0, initial position, and theta 1. And you have to decide the time as well, right? How much time you want from here to here. I mean, the shorter it is, that means you're moving faster. You're moving faster. That means from here to here, you're moving very fast. So do you want to move it slowly from here to here, or you want to move it fast? It depends on the selection of time here. All right, so theta 1, theta 2, theta 0 and theta 1, sorry. Next, the same lift-off requirements for the arm motion is also true for the set down point of the final position motion. That is, we must move to a normal point out of the surface and then slow down to the final position so that the correct approach direction can be obtained and controlled. Okay, that means from here you move up to the lift off position, and then you have to move to another position that we call set down. Again, this is to avoid hitting the fixture if we have any. Okay, so from here we'll be moving. So number 3 is sorry. My digital pen is going crazy. Sorry, I cannot write it down, so I'll just try to talk for now until this becomes okay. All right. So this is set down. Sorry, still not okay. So this is set down position. Theta 2. Okay. Once again, I'm sorry for the horrible handwriting because something is wrong with my digital pen thingy. So I'm not even touching
It's okay, Doctor.
Okay. I'm not even touching the tablet, but it's still writing. Anyway. Okay, so we have set down position, theta 2. It is here, right? So this is a slightly wrong notation. I will try to explain shortly. So this is theta 2, and then we have finally our theta f, which is the final position. Okay, that's about it. Okay, once again, right? So we have. So the goal is we are trying to design a trajectory or a path, right? So the situation is we're going to pick an object from the pick location. So this is the pick location. The object is here, and the object is at a fixture, right? The fixture holds the object. So we cannot pick and just move right away to the place location because it will be damaging the fixture, maybe, right? So normally we would move out normal to the surface, straight out to here. So this is what we call the lift off pose, or if you talk about angle, it is the lift off position, right? And then from here you move to the set down position, and then from set down position you will slowly lower the object to the final location. Okay, and I've explained earlier that when the robot moves, we can plot, you can view the trajectory of each angle, right? Theta 1 up to theta n. Maybe it looks like this. So for every joint you would have theta 0, theta 1, theta 2, and theta f, because the robot will, when the n effector moves from here to here, all angles probably will change. So this is really a vector. this is theta 0, 1 for joint number 1. This is for joint number 2. Up to theta 0 joint n, the last joint. Okay, so by right, I should be writing theta 0, 1 because this is the first joint, or first theta 1, right? And this is theta 0, 1, 1, 2, 1, and f1. So this is really theta 1, 1, theta 1, 2, up to theta 1 n. So the first subscript here refers to the initial position, and the second number refers to the joint. So this is joint number 1, joint number 2, and up to joint number n. And similarly, the first number here, the first subscript, refers to lift off position, right? So everything here, the first number is 1, and the second number refers to joint. So this is joint number 1, joint number 2, and joint n. So the same thing for the rest as well. So this is f1, theta f2, up to theta fn. Okay. So from the above, we have 4 positions for each arm motion: initial position, lift off position, set down position, and final. So if we, for example, this is joint number I, right? Like I said, we have this path for every joint. So if you focusing on joint number 1, and this is so this should be theta 0, 1, theta 1, 1, theta 2, 1, and theta f1. Okay, so this is how each joint will move. So we'll start with the initial position, we'll move towards the lift off position, and then set down and final. And similarly, we have to determine the time as well. So the shorter it is, that means you are moving faster. So some constraints. In initial position, the velocity and acceleration are given, and normally they are 0. Okay, so you can imagine when you pick an object, the velocity and acceleration at that time is normally 0. So if no acceleration is given to you in a question, or no velocity, understood, the values are 0, right? And during lift off position, it should be continuous motion for intermediate points. And for set down, it's same as lift off. And final position, the velocity and acceleration are given. So what does it mean is that, let me try to open a new canvas. So for example, so let's talk about theta 1. So we have the initial position, lift off position, this is set down position, and this is final position, right? Remember, the second number is referring to the join, first number referring to 0 for initial, 1 for liftoff, 2 for set down, and F for final. So at this point, let's call this tau 0. This is the initial time. This is the set down liftoff time. This is the set down time, and tau F is the final time. Okay. So here at this point, normally the velocity is 0 and the acceleration is 0. That means you start picking at 0 velocity at a static configuration, right? And the same thing here. So at this point, when you place the object at the final position, the velocity is 0 because you're placing it, right? Unless you want to drop as you're moving, it depends on the application, but normally the final velocity is 0 and the final acceleration is also 0. And we want to design a path from here to here such that it goes through or traverses all the points in a continuous, smooth manner. So you don't want to design a path like this, right? This is not continuous, we call, right? This is discontinuous and not smooth. So a continuous one will be smooth and it follows every path, right? This is more or less continuous. So we have to keep that in mind. And we have to take care of the time considerations as well. So for initial and final trajectory segments, in this segment here, this is initial segment and final segment, time is based on the rate of approach of the hand to and from the surface and is some fixed constant based on the characteristics of the joint motors. So if you refer to my explanation earlier, this portion right here from initial position to lift-off position is when we lift an object from the fixture and move straight out of the surface, right, in a normal fashion, right, in a normal direction, right? And once again, we do that to avoid damaging the fixture or hitting it, right? So usually we do this slowly. Okay, so and the time from tau 0 to tau 1, it's normally we fix it. Maybe you want it to be 5 seconds or 3 seconds. You fix it depending on the operation. And the same thing here, right? From tau 2 to tau f, or in other words, tau f minus tau 2, that's the time. Let's say 3 seconds. It's a constant that you decide based on the application. It also depends on the motor. So can your motor move from tau 2 to tau f in 3 seconds, right? So if you can, then you keep it as a constant for every joint maybe, right? However, from tau 1 to tau 2, you can move it very fast, right? Because you have cleared here, you cleared the fixture, and here again you will not be hitting the fixture. So from tau 1 to tau 2, assuming there are no obstacles, you can move very fast. Okay. So the intermediate points or mid-trajectory segment, time is based on maximum velocity and acceleration of the joints, and the maximum of this times is used. That is, the maximum time of the slowest joint is used for normalization. So now we're talking about this tau 2 minus tau 1, how fast you want to move it. So once again, let's So here we have a robot. Let's say we have 4 joints, right? Joint number 1, joint number 2, joint 3, and joint 4. So when you build a robot, of course these joints would be actuated by motors, right? And you won't be using the same motor for every joint, because that would be either not practical or it'd be a waste of money, right? Why not practical? Because you know that joint number 1 takes the most load, right? So joint 1 has to be actuated by a powerful motor, and the same motor here you will not be using it here, right? Because here it just carries the end effector, and probably it doesn't have to be that much strong or powerful. So different joints have different motors, and therefore they have different angular velocity capability, or the maximum angular velocity or angular acceleration that it can achieve. And normally when you move a robot arm to pick and place an object, you want all the joints to move and stop at the same time. It is more to like an aesthetic view, or it's also to so that you don't damage the motor, the robot. So you want all joints to move and stop at the same time. Okay. So therefore, this time has to be the maximum of the slowest time. What does it mean, right? So let's read again. Time is based on maximum velocity and acceleration of joints, and maximum of this times is used. The maximum time of the slowest joint is used for normalization. So you have to select a time such that all joints can cope. If you select too short of a time, maybe joint number 1 will not be able to achieve, because joint number 1 has a high torque but maybe a slow response time. So you have to select a time such that all joints can achieve the time. All right. So based on these constraints, we are concerned with selecting a class of polynomial functions such that the required joint position, velocity, and acceleration at these knot points, which is initial, left off, set down, and final positions, are satisfied. And the joint position, velocity, and acceleration are continuous on the entire time interval. Tau 0 is the initial time, and tau f is the final time. And one approach is to split the entire joint trajectory into several trajectory segments, so that different interpolating polynomials of a lower degree can be used to interpolate in each trajectory segment. So once again, we have a few constraints, right? So we want to design a trajectory for every joint of our robot arm, and we have a number of constraints. The constraints are the trajectory has to go through initial position, lift off position, set down position, and final position in a continuous manner, in a smooth manner, right? That's constraint number 1. Constraint number 2, we have this time. It has to achieve or reach these positions at specific times, and these times depends on the operation and or depend on our motors, right? Like I said, if you select this time to be too short, maybe your motor could not handle because your motor is small and it moves slowly, right? We also have the third constraint, which is the velocity, right? Like I said, normally the initial velocity and initial acceleration 0, and similarly the final velocity and final accelerations are 0 as well. But that is not always the case depending on the application. But for a simple pick and place operation, yes, those velocities and accelerations are 0. Okay. In order to achieve those constraints and in order to have a smooth trajectory, normally we would break down the whole trajectory into a number of trajectories, and then we design a polynomial for each segment. Okay, so there are different ways a joint trajectory can be split, and each method possesses different properties. The common methods are 4-3-4 trajectory. So this is what we will learn in this course. Each joint has the following 3 segments, right? And the first segment is a 4th degree polynomial. So this segment is a 4th degree polynomial. The second segment is 3rd degree polynomial. Second segment, 3rd degree polynomial. And the final segment is 4th degree polynomial. So this is what we call the 4-3-4 trajectory. And there's also another design that we call 3-5-3 trajectory. It is the same as the 4-3-4 but uses polynomials of different degrees for each segment. So in 3-5-3, the first segment is 3rd order polynomial. Second segment is the 5th order or 5th degree, and the last segment is 3rd order polynomial. And then we also have the 5 cubic trajectory, where we use 3rd degree polynomials for 5 trajectory segments. So in 5 cubic trajectory, rather than splitting the trajectory into 3 segments like what we have here, we would split this trajectory into 5 segments. Right? You can imagine there are 5 segments, and each segment uses 3rd order polynomial. So now if I ask you, what is 4th degree polynomial? What do you understand by 4th degree polynomial? Okay, my pen seems to be okay now. What is 4th degree polynomial? And it would look, because our x-axis is time, right? So it will look something like this. We have some terms here, and the highest power is 4. This is 4th degree polynomial. Then we have a term, usually a number here, right? 3, 2, 1, and something, and a constant as well. So this is 4th degree polynomial. So if you have a 3rd degree polynomial or 3rd order polynomial, the highest order will be 3. Okay. So for 4-3-4 trajectory means this line here will be a 4th degree polynomial. This line will be 3rd degree polynomial or 3rd order, and this again will be a 4th degree polynomial. Okay. So next, let's look at, before we look at 4-3-4 joint trajectory, let me ask you, right? So what are the steps in order to design trajectory for a robot arm? Okay, first of all, I don't want to ask you because some of you don't have mic. Maybe you have internet problem. Sometimes my internet is problematic. So I'm recording this, and I hope I can upload this later. But I'm going to explain to you anyway. What are the steps, right, that we have to carry out in order to design the trajectory? Number one, we have to determine the determine what? Initial and final pose, right? Initial pose, let's call this T0. So this is the homogeneous transformation matrix of the n effector. The initial pose and the final pose. Tf of n effector. Number 2, we have to determine the lift off pose. This is a homogeneous transformation matrix, and set down pose. Set down pose. T2. So we have 4 homogeneous transformation matrices. Number 3, using inverse kinematics that we have learned in the previous chapter, we should compute data initial position. This is a 6x1 vector, right? For every joint, the lift off position or the angle, set down position, and the final position of every joint. So each of these is a 6x1 vector. So we compute this using inverse kinematics. And then finally, you can compute the path. So if you are designing the 4-3-4 trajectory, you have 3 segments. So compute h1 of t, which is the 4th order polynomial. Compute h2 of t, 3rd order polynomial, and h3 of t. T is time. Again, this is the 4th order polynomial. So this is 4th order polynomial, 3rd order polynomial, and 4th order polynomial, if we are using 4-3-4. Right? What's the time now? Time is almost up. So let's quickly look at a simulation, if I can show it to you. Oops. So this is MATLAB. We will learn how to do the simulation when the time comes, but for now just look at it. So we have some coordinate frames here that shows the initial pose of the n effector, the red one initial pose of the n effector, the green one is the lift off pose of the n effector. Again, this green is the set down, and the final red is the final position or final pose. Okay, so that's all for today. So when you saw the robot moves from coordinate frame 0 to coordinate frame A to coordinate frame I don't know what I labeled, and then finally to coordinate frame F. That is the whole trajectory planning operation that we will be learning in this course. So do you have any question?
No, sir.
All right, so if you have no question, that's all for today. I'll see you again on Sunday. Thank you very much.
Thank you, sir.
Thank you.
Doctor,
Yeah.
I have a question.
Yes.
So if like on the previous chapter, we are learning inverse kinematics in finding the first three positions of
Yes.
the theta, right?
Yes.
And then for this chapter, we need to find the final theta.
Yes.
We need to learn something else to find the final theta.
To learn the what? Final
position means the theta of the final joint, I think.
No, it's like this, right? Yeah, indeed, in the previous chapter, we only learned theta 1, theta 2, theta 3.
Yeah.
The reason is because I don't want to load you too much, or else you'll be overloaded with equations.
Yeah.
So because the idea is that if you know theta 1, theta 2, theta 3, then in the future you can learn yourself how to find, or you can find equations, you can use MATLAB toolbox. There are many tools out there to find all the theta from theta 1 up to theta 6. But you are right, for trajectory planning you need theta 1 up to theta 6 because you have to find the initial position which has 6 angles, and the same thing with initial. We have lift off, set down, final position. They are all 6 from first joint up to 6th joint. So in your exam, the thetas will be normally given. So even if you have to compute, you have to compute from theta 1 up to theta 3 only.
Oh, okay.
So you don't have to compute the joint angle for 4, 5, 6. You don't have to.
Right. And there is another question.
Yeah.
About. I'm sorry to ask now because it's actually from previous chapter.
Sure.
The elbow in the lecture video. Why is it -1? Because I try to find the. I already found the paper where you refer to, but I cannot seem to understand why the elbow is -1 when the arm is straight.
Oh, okay. Let me share. Do you have time? Do you have another class after this?
Yeah, I have another class.
Okay, let me quickly show you. Okay.
Okay.
You can see my screen, right?
Yes.
So let's look at the definition, right? The elbow definition. So why it is above, why is below, right?
Yeah, very confusing when the arm is straight. I cannot understand.
When the arm is straight. So when the arm is straight, what happens? Position of the wrist of the right, or we are talking about left, right? Left or right?
In the example is left arm.
Okay. Position of the wrist of the left arm with respect to the shoulder coordinate frame. You can ignore the shoulder. This phrase has negative y2. Has negative y2, right? So where is y2? So this is x, y, z. Y2 is downwards.
Yeah.
y2 is downwards. So the wrist is, this is the position of the wrist.
Wait, I cannot see your pointer. Yeah, I saw it now. Yeah.
So this is the wrist.
Yeah, okay.
Okay, this is the wrist, and the wrist is along, you can imagine it's along Z3.
So it's along that tree.
Yeah.
So it's not in the same position with same level with x2.
No, because you have to know what is x3, what is Z3, right? Z3 is the axis of rotation of joint number 4.
4, yeah.
So this is joint number 4, right?
Okay.
This is joint number 4.
Oh, okay.
So you can imagine the wrist should be, the position of the wrist should be along the axis of joint number 4. Therefore, it is along Z3.
Oh, okay, so the Z3 is actually telling the frame of the wrist, the wrist joint.
Yes. So,
Okay.
so the origin of coordinate frame 2 is over here, right?
Mm-hmm.
So the wrist is negative y2, because up here, because
Wrist.
so y2 is down here. This is the origin. Y2 goes downwards.
Okay.
Can you imagine? This is origin of coordinate frame 2. Y2 is downwards.
Yeah.
So the wrist is negative y2.
Oh, okay.
So so that's why it's below arm,
Okay.
because the position of the wrist has negative y2 value.
Oh, okay. I understand now, because there is two origin at the that point, right? There is two origin. One is below, which is the elbow,
Yes, exactly.
and then one origin is for the wrist and is slightly above the elbow origin. So that's why.
Yes, it's given by A3, right? So A3 is negative, you see?
Mm-hmm. Okay.
Yeah.
Okay. Thank you, doctor.
Yeah, so try to digest a bit, and then if you don't understand still, you can ask me another time.
All right. Okay.
Okay,
Thank you, doctor.
welcome.